Let's get started. Good afternoon, everyone. I'm Ram Podal, a researcher here at NREL. Thanks for joining us this on-demand webinar, a part of the wind workforce development effort here at NREL. Today, we are here with another webinar of this series. Our presenters are Tom Acker and Greg Stark. The topic is Integrated Energy System at Scale, Wind and Hydro Integration. This webinar is being recorded. It should be available in our NREL Learning channel in about 2 weeks. Tom Acker joins us from Flagstaff, Arizona. Greg Stark here from NREL Flatiron campus in Boulder, Colorado. Tom Acker led IEA Wind Task 24 on the behalf of NREL. IEA Wind Task 24 focuses on the integration of wind and hydropower systems. Greg Stark is Hydropower Technical Manager and Water Power Grid Integration Lead here at NREL. As a part of his role, Greg leads Operation and Planning Research Area for DOE's new Hydrowire initiative. Educational tools and curricula to support university education are part of NREL Wind Workforce Development effort. This NREL project aims to enhance classroom activities at Wind Application Center and University. Integrated Energy System at Scale, IS in short, continues to be a focus area of NREL research going forward, especially at our Flatiron campus. IS aims to enable high contribution of renewable energy in our power system. As the contribution level of renewable energy in our power system is growing, we need to come up with novel ways to enhance capacity value of wind turbine, wind farm alike. The Vulnerable Power Administration, a part of DOE, is helping many wind developers in the Pacific Northwest in order to absorb the variability in wind. Innovation in fast-acting ternary pumped storage hydro technology helping bring us more renewable energy online. Absolrosa Energy currently developing 400 megawatt Golden Boot pumped storage hydro in central Montana. I believe that project recently got financed. GE Energy demonstrated wind turbine with built-in hydroelectric batteries in Germany. A lot of new and exciting opportunities ahead. I'm sure our presenters today will elaborate them. We'll try to make this interactive series as possible. Please use the chat feature on Zoom so that you can submit your question to us. Please go to chat and type your question there. You have an option of asking the question to everyone or a specific person. Please direct question to everyone. My colleague Tan might merge them together. In any case, please keep your question coming. We'll have about 10 minutes for question and answer in this hour-long webinar. With that, I'm going to pass it to Tom. Tom, here you go.
Thank you, Ram. I am going to share my screen and start up a presentation. So it's a pleasure to be here speaking with you all today. And what we're going to be talking about is wind and hydropower integration. So really, that's the integration of these clean energy resources to meet society's electrical needs. So I'll be starting us out in this webinar, and I'll be talking really about what is wind and hydropower integration. When we talk about that, what do we actually mean? And so I'll lay the foundation for hopefully understanding the results from a few recent studies, which is what Greg Stark will be talking about. So we're going to do a little tag team in our presentation today. The outline of the presentation, we'll start with hydropower in the US, just to give you a picture of hydropower and its complexity. We'll talk about wind power and the nature's delivery of electricity and how that influences operation of the electrical system. Give a brief overview of the electrical system and then how it's balanced. So how do we make supply meet demand? And then we'll talk about the role of wind and hydropower integration in the electrical system and how we simulate that using production cost modeling. And with those basics, we'll go into some recent project results, and that's what Greg will talk about. Okay, we'll start with hydropower in the US. So first off, good source of information on hydropower, just go to your Google search bar and put in DOE hydropower, and up will pop a site with a lot of good information about many aspects of hydropower. This picture of the dam that you see in the lower left, that came from that site. And this report cover you see on the right side, the 2017 Hydropower Market Report, that is available at the site, and that's something that's updated routinely at the Department of Energy. That report has a lot of good information about hydropower, so I definitely recommend taking a look at that. This picture of the dam on the right side shows many of the pieces of a hydropower dam. I'm going to focus on the water coming down through the dam going into the turbine. So there's a few different kinds of turbines you use in the hydropower dam, but you can see there's a pretty direct connection to the reservoir. And there's some gates, some wicket gates that control the flow of water from the dam into the, down the penstock and into the generator. And that allows you to turn up and down the hydropower generation fairly quickly, depending on how the hydropower dam likes to operate. So I just want to kind of point that out. There is a lot of momentum in that water and inertia in the rotor. So you can't necessarily change it instantly, but it does respond very quickly to changes in the load. Okay, we'll see more of that a little bit later. Oak Ridge National Lab has a really nice site for getting information about hydropower. And if you go to your search bar on Google and type ONRL Hydro Source, up will pop their website with a lot of good information. This map I'm showing you on the right is from that website, and it shows hydropower, the National Hydropower Map for the United States. So you can see where the hydropower exists. In the east, there's many smaller hydropower plants all through the Appalachians up in the northeast. In the west, it's in the mountains of California, along the Columbia and Snake Rivers up in Oregon and Washington, the Missouri River through the north central states, Colorado River down through the southwest and in the Rockies, and along the southern Mississippi. So you'll see a lot of the hydropower here. Conventional hydropower is a hydropower plant with impoundment or with a dam with water storage. So you can see this picture of the Big Bend Dam in South Dakota that's on the Missouri River. It's got a lot of impoundment. It's run by the United States Army Corps of Engineers. This plot you see on the left, this bar chart, this shows U.S. conventional hydropower fleet. So what I did is I went into the Energy Information Agency and I got their Form 860 on annual generator report for 2018, and I filtered through that to get some statistics about the conventional hydropower. And according to the EIA, we've got 79 gigawatts, so 79,911 megawatts of conventional hydropower spread across a little over 4,000 generators, 2,200 different hydro plants in 48 states. The hydropower market report shows 2,241 plants, about 80 gigawatts again, so fairly consistent. So this Big Bend Dam, it has a pretty fair amount of storage on the Missouri River. Here's another dam that has a lot of storage, even more in this case, and this is Hoover Dam on the Colorado River. And you can see down in the lower right, it's connected to Lake Mead, and that's a very big reservoir. So there's months of water storage in this reservoir. You can also see it's a very tall dam, so it can produce quite a bit of power. It's got a high head, and you can, excuse me, get back up to that. You can see there's a little bathtub ring around the reservoir, and that kind of demonstrates that the water level happens to be low right now. Okay, next picture is of the Wanapum Dam on the Columbia River. So this dam is about 1,000 megawatts. So it's got a lot of generation, but you can see it sitting on the Columbia, and there's not a lot of reservoir here. So this reservoir really has hours of energy storage versus months like you have in Lake Mead. And if a hydropower facility does not have water storage or very little, it's generally called a run-of-the-river dam. So you go from a lot of storage, tall dams, you've got this case of Wanapum, which has got several hours of storage and not as tall of a dam. So the facility and the characteristics change depending on the water system. What we're looking at here is a pumped storage hydropower plant on Lake Michigan. And the lake, I believe, is the storage reservoir there, the Ludington Pumped Storage Hydropower Plant. I think it's about 100 feet above Lake Michigan, which you see on the bottom part of the picture. So that's a fairly large pumped storage plant. Pumped storage plants are really built for energy storage. And what you would typically do is when the energy costs are low, you've got excess generation, you pump. You fill up the reservoir, and when energy prices are high, you release. So it's really a big energy storage facility. The plot on the left, the chart on the left shows that we've got about 22.8 gigawatts of pumped storage hydropower in the US. That's in about 40 projects spread across 18 states in the US. This map shows the federal hydropower. So the biggest conventional hydropower plants and some of the biggest pump storage are federally owned and operated. I've got three different maps here. One is USACE, US Army Corps of Engineers, and you can see where their hydropower is. You've got the Tennessee Valley Authority in the middle on the bottom there, and the US Bureau of Reclamation, which runs some very large and many plants in the western United States. So in terms of the complexity of hydropower, thinking about it as an energy supply on the grid, you've got federally owned facilities, many. There are also many other public facilities that are not federally owned. In fact, more facilities are non-federal than federal, but much more generation is federal than non-federal. So federal hydropower is an important contributor in the electric system. That federal hydropower is typically sent to its loads, its customers, through federal power marketing agencies. So the four shown here are Bonneville Power Administration in the Northwest, Western Area Power Administration through the rest of the West, the Southwestern Power Administration in the Central West, and then the Southeastern Power Administration in the Southeast. So in terms of a complex system, you've got federally owned hydropower that is then transmitted to the customers through a federal transmission system to the customers themselves who have their rights to that power. Okay, this is a picture of the Columbia River Basin, which is where Bonneville Power Administration distributes the power. And there's Corps of Engineers dams, there's US Bureau of Reclamation, and then there's several public utilities that are up on the Columbia River and Snake River. That red circle, that oval you just saw up here, that's the mid-Columbia River. And the white triangle there is Grand Coulee Dam. It's at the head of that mid-Columbia where you've got several dams. The water passage time from Grand Coulee down to the bottom when you're, so Grand Coulee on the top, Priest Rapids on the bottom, is several hours. So like half a day or something of that sort is about the time it takes for the water to flow. So what comes out of Grand Coulee very much influences what comes out of those other dams. They can't generate unless Grand Coulee generates and passes water. So there's a connection. So there's an interconnected river system, and you have to manage that so that everybody on the dam can produce the most amount of power while managing the water. Okay, this plot on the right here shows the discharge from Grand Coulee during a week in 2001. And you can see how the discharge, the dark blue lines going up and down as Grand Coulee generates not much at night and a lot during the day, during the peak hours. That red line in the middle is the discharge from Priest Rapids downstream. And you can see that's very constant. So what happens between Grand Coulee and Priest Rapids is that distribution of water is re-regulated. So what comes out of Priest Rapids is very constant. It comes out constant because south of Priest Rapids, there's a free-flowing stretch of the Columbia River where a lot of salmon spawn. And so there's some environmental regulations that really make it precise in terms of how the water comes out. So Priest Rapids doesn't have much flexibility, whereas Grand Coulee does. Here's an example of Hoover Hydropower from 2007 from their SCADA system. So this pink line shows the total capacity available. So they had about 1,200 megawatts available that particular day. online and ready to generate was a little under 900. So the difference between the online and the total capacity is a non-spinning reserve, is what we would call it. Down here on the blue line, you see going up and down is the actual generation. So you can see that's actually moving up and down quite a bit. So it's got a bit of flexibility on what it produces that day. And this green line shows the spinning reserve. So that's the difference between the online capacity and what's actually being produced. And so that's a reserve available to use on the system. That's flexibility. Very big contrast between that and Priest Rapids. In terms of hydropower availability, we think of as energy resource. This plot on the left shows projected elevations for Lake Powell at the end of months over several months. And you can see that as you go from the black line, which is when this plot was produced and you're projecting ahead of time, there's quite a bit of uncertainty in terms of exactly what precipitation you're going to get. So the availability could be greater or less than depending on what actually happens. On the right, we see the production from Glen Canyon Dam, which is the dam at Lake Powell, for a couple different years. And these are the daily energy production. And this daily energy production, you can see these little bumps as it goes along here. Those are weeks through the year. So you can low generation on the week and high during the week. You can see 2013 in blue had more generation than 2014 in green during certain months, but not in other months. And you can see the months that generation amount changes from month to month, and that's due to water deliveries for irrigation downstream and some environmental concerns of flow through the Grand Canyon. Here's a picture of Lake Mead from 1984 to 2016, and you can see how the water changed quite a bit in that period of time. So that's an issue of hydropower availability when you think about using it as a grid resource, integrating other sources of power. This plot, or not this plot, but this slide talks about the order of priority for hydropower facilities. So typically flood control is the top priority. You got to save the structure and try to not let floods occur downstream. Fish migration, such as you saw in that Priest Rapids generation or that discharge, is like fish migration is important. Our environmental considerations. Dams need to be environmentally compatible in their impoundment and the hydropower. Irrigation is important. In fact, that's what runs the show for water deliveries out of Hoover and out of Glen Canyon. Recreation lake levels, so on holiday weekends, that's important, and that'll dictate the power generation or what water is available for it. And navigation can too. So power production is often the lowest priority. Excuse me, get back to that dam. It's usually the lowest priority of the things that a hydropower facility will do. Okay, let's talk a little bit about wind power. The Wind Exchange website run by the Department of Energy is a great site if you need wind energy information. So I'd recommend you check that out sometime. Through the Department of Energy, Lawrence Berkeley National Lab, they produce a wind technologies market report each year. And the most recent one shown there from 2018. So these market reports have great information about utility scale wind production. And I definitely recommend you check it out if you haven't before. This plot, for example, is from that Wind Market Technologies report. And it shows the change in wind power generation since 1998, when there was very little utility scale wind power, to now when we're looking at nearly 100 gigawatts of wind power. That's more than that's approximately what we have in terms of hydropower, conventional plus pump storage. So it's a mainstream energy resource. This shows the variability you might get from a wind power plant. This is over a 20-minute time period, but I want to give you a sense for the variability in terms of the wind speed, which you see on the top, which can vary by about 30% across this 10-minute period. If you look at the power output from one turbine, a turbine has inertia, it can't respond quickly to the wind. So that red line shows the variability of a single turbine. And if you had 35 turbines at that site, you would see how that variability in the wind is effectively smoothed out. And so that's something to consider about wind and how it's variable. So that's inside a short-term 10 minutes inside a wind power plant. This shows how wind power plant output is correlated. The horizontal axis is kilometers, so you can see we go from 3 to 1500, it's a logarithmic scale. And the correlation coefficient between wind power plant output at different wind power plants on different time scales. The bottom line on the blue shows that there is very little correlation, no correlation between wind power plants on the 1 second output. When you talk about 1 minute output, very little correlation. When you get to 10 minutes, now if the power plants are close together a few kilometers, you're going to have a correlation. And the hourly output is certainly correlated for wind power plants that are not far away. So one goes up, the other one's going to go up soon. One comes down, the other will come down soon. But as you get to be, say, a couple 100 kilometers apart, the correlation is low on the hourly time frame. Wind power forecasting is important. So wind power is variable. It's going to influence how we need to balance the electrical system. So forecasting that wind power is important. And the plot here on the left shows the mean absolute error of wind power forecast. I'll just focus on the bottom line here. This is a professional forecast from a wind power forecasting firm, and you can see inside 10 hours of when the wind's going to happen, that error will be, say, in the order of 5%, goes up to about 10, 15%, depending on the forecast in the area within 10 hours. And as you forecast out over the course of 40 or 50 hours, that forecast error goes up to, say, 20% mean absolute error. So you can forecast the wind with some accuracy. The plot on the right shows the hourly change in output from a wind power plant, its mean absolute error. And really the upshot of this plot is that while we may have a 5% error on the 1 hour forecast, that error is really low when the wind isn't changing, and it grows somewhat when a wind is changing. So when you might have a front coming through. So we are going to have forecast error when the wind is changing. Let's talk briefly about the electrical system. U.S. electrical system is broken into, really, the North American electrical system is broken into 4 different regions. The Western United States, the Western Interconnection, Texas, the ERCOT interconnection, the Eastern Interconnection, and then Quebec. So these interconnections are where every generator is in sync, online in sync, and electrically interconnected with one another and with the loads. This is a FERC plot showing the balancing area authorities within that region. So every one of these little circles here, these little white circles on the map, that represents a utility, a group of utilities, where they have to make load meet demand. So they're responsibility for balancing load and demand. And they have to manage the frequency and the voltage to keep the system reliable. So there's many of these balancing area authorities. The balancing area authorities use reserves to balance the system. So when you've got load and generation and they don't match, then you need to use your reserves to make them match. And so you have non-event actions, regulating reserve, following reserves, and you have event reactions, reserves for when you aren't expecting a change. So you have reserves set aside specifically to anticipate things like the daily increase or decrease in the load. And then the events are for when you might lose a transmission element. We also have a number of different ways to deliver that electricity. There's vertically integrated utilities, which exist in the white areas of the map, where you have a regulated monopoly, and you have markets throughout the United States, and this shows several of those markets. So the market system actually has a big influence on how you can use your hydropower in the grid and how the wind power comes into the grid. So how do you balance all of that? Well, if we look at the load through a day here, there's some very short-term, minute-to-minute, second-to-second changes popping up and down. We would tend to call that regulation. Load following these big swings as the load goes up in the morning or afternoon. We have to schedule our units during the day and dispatch them. And we have to commit units sometimes days ahead, depending on the coal-fired power plant is committed days ahead when it's going to be used, whereas a gas power plant can be committed within the day. So unit commitment is one of the ancillary services, one of the functions we do when we try to balance load and demand. This plot shows a couple wind power plants, 100 megawatt wind power plants in the Midwest, and it shows their variation. So these little bumps up and down minute to minute, that affects the regulation on the system. The big ramping of the wind power plants as fronts come through, that affects load following. Unit commitment is affected by when the wind is going to be there or not and what you forecast. And do you have system adequacy, long-term planning? What can you count on from that wind power or the hydro? You can get wind in the middle of the night and you might not need it. Can you store it or do you curtail it? And so looking at these particular variations, are they significant? It really depends on the system in which it's being integrated into. Okay, the role of wind and hydropower. So this is from the Western Wind and Solar Integration Study back in 2010, and this shows for the Western Interconnect, a subset of that, 30,000 megawatts of load. So this is a lot of load in the spring. So that top line shows the load through a week. The red, the yellow, and the green are the renewable energy resources in this particular study. So there was a very large amount of renewable energy, 35% on the course of the year in terms of the energy. But you can see during this particular day on April 15th, there was more renewable energy than there was load. And the net load is the difference between the load you get and the renewables which you bring into the system. And you can see that net load is somewhat more variable than and less predictable than the load itself. And so that's the challenge when you bring a lot of renewable energy into the system. So it influences that unit commitment, load following, the regulation, and the amount of reserves you need. So here's looking at a week similar to that week in the dispatch stack. So you see nuclear on the bottom, steam, coals, the dark blue, gas, and then hydropower is right on the top there, kind of topping it off, is a peak shaving type resource. This is when you've got all that renewable energy, and you can see it's very different. How the hydro is used is very different. And given the complexity of the hydro system we just talked about, can you do that? And is it worth it to the hydropower? So the questions we want to answer, and I'll be jumping over to Greg here in a moment, is what's the impact of a large-scale wind and solar, but certainly large-scale wind in terms of the ancillary service you need and how you balance the system? And what's the ability of hydro to address these impacts based on its physical resources, its impoundment, does it run to the river, its operational flexibility, its environmental constraints? What are the economics? What's the value of those ancillary services and the energy? And is that of good value to that hydropower plant? What's the value of that energy storage? And it's different whether you're in a market system or a vertically integrated system. And the answers to these questions really depends on who's asking it. So how do we answer these questions? We use production cost modeling. So a production cost model is a computer model that is basically built to simulate operation of the electrical system, all the generators, the transmission elements, and the decisions that are made in terms of committing and dispatching those. You see on the right here some of the popular and well-used production cost models. Plexos is the one that Greg Stark will be mentioning, Power System Optimizer, PSO, GE Maps, ProMod. These are a few, there are others. And this last picture I'm going to show you is just a 5-bus system. This shows 5 different, I guess, 1, 2, 3, 4, 5, 6 different transmission lines and 5 different buses and generators attached to buses and loads attached to buses. I show you that simply because that's what lies beneath the production cost model. That was a simple 5-bus system, but under a big production cost model, for example, the WEC, the Western United States, there's thousands of generators and buses. All right, now I get to hand it over to Greg.
Okay, great, thank you. So what I'm going to be talking about today is kind of these 4 different things, give a little bit of background just to set this up, and then 3 different studies. The first is going to be where we have like 47% penetration of renewable energy. and looking at kind of the interaction of wind and storage. The second is about kind of the time scales, and that's a higher penetration up to 55%. And then the third one is an area where we really could use your guys' help because it's an emerging area for research, and that's looking at systems that go all the way up to 100% renewable energy. And all three of these areas, they're very closely related to, Ram had mentioned earlier my work with Hydrowires, and that's a new initiative at DOE where it's looking at hydro specifically from the perspective of the grid, how does it fit in particular hydro as essentially a renewables enabler. It's one of the few technologies that matches really well with wind, that has kind of longer duration storage and the high capacities that match well with the big wind farms. And I have borrowed slides from a number of colleagues here throughout the lab, and so you'll see at the bottom here, I just mentioned them as we go forward. The first, and I'm not going to spend much time here because Tom, I think, did a nice job on kind of setting it up, but the key thing on the grid that I want to mention and why hydro, and well, any type of storage, but pump storage hydro in particular is important, is the way the grid works is pretty much supply has to equal demand. There's only a very small amount of storage there. And so what storage you do have becomes very valuable to let you offset some things. And then the other thing that I wanted to mention from this particular slide is renewable energy can complicate things because there's variable generation with that. And it can be weather dependent. In particular, think of a big solar farm as a cloud passes over, those types of issues. But the good news for that, from the hydro perspective, this is actually an opportunity because hydro is pretty quick at responding to things. And this research is built off of kind of past work that we have done here at NREL. And I mentioned the renewables penetration that we're looking at in this first study is 47%, so 35% of that wind and then 12% PV. And the real takeaway on this particular slide is, look at the map off to the right side there, and it shows kind of the average wind penetration. And look at where the large amounts of wind are versus where the population centers are. Think about where do most of the people live. If you had to pick one place, it would be Southern California, right? And so the wind is up in Montana and in Wyoming. And so to set these studies up so that you don't get kind of false results on the value of pump storage hydro, the first thing you need to look at is transmission. Because if there's no transmission, it would be built because it would just be uneconomic not to. And so we looked at 3 different transmission scenarios and how that would impact curtailment. And that's what you're seeing in the lower left corner of the screen. Is, the first line is reference, and you have about 16% curtailment right there. And so that means you're throwing away 16% of your renewable energy, and that's just uneconomic. So they would build out transmission, and then you can see the scenarios as you add, a little over 10 gigawatts. It cuts curtailment by half, and then it's kind of diminishing returns as you go up to the 21.5 gigawatts. And then the last item you'll see is copper sheets, and that would be if you had all the transmission you could ever want there. And just as a perspective, this system, the peak on it in summertime tends to run about 150 gigawatts. So that just gives you an idea of kind of the magnitude of the numbers we're talking about. Okay, so this is where we get into looking at pump storage hydro and the role that hydro can play in with wind. And I mentioned there as far as transmission, and we would expect some build out to get costs down, but what's the optimal mix? Do you do everything in transmission? Do you try to do it that way, or are you smart about it and use some storage? And in particular, pump storage hydro is great because it's very high capacity, and so it can allow you to build out maybe not as robust a transmission grid as you might otherwise, but you can make sure that that transmission line stays full, so that you're getting the most use of it. And the reason that's important is transmission is really tough to site. If you try to cross several different states, each state regulates its own boundaries. And so you have to get buy-in from a number of people to make this possible. So what we looked at is, in those three scenarios that I talked about earlier for transmission, adding storage at the site of generation. And you can see here on these, we added 2 gigawatts in Montana and 4 gigawatts in Wyoming. And so this is between about 1.5% to 3% of the peak. As I mentioned before, it's about 150 gigawatts in summer. And just as reference, winter, it tends to be the peak in this area, although it doesn't go down to Southern California. It tends to be up and more in the Northwest, is about 126. So the other thing is we chose to look at 8-hour duration storage and 80% round trip efficiency, which is pretty typical. The duration is a little bit shy on what pump storage. You might see more up around 12 hours and things that are out there, but the 80% is quite typical of what you can see today. Some of them can even get up around 83% in some of the Turner units. So this plot shows how, kind of the synergies between storage and transmission. And you can see in every case, by having storage available at the generating point, it reduces curtailment. The one thing that we did notice here, and it's left kind of for future research, is wind could actually benefit from maybe a little longer than 8-hour storage, because there are some time periods where there'll be a lull in the wind. And then the last is just the max capacity factor on this particular unit, although it doesn't run that high, or the storage we were looking at, it was several, is about 40%. And the reason, what drives that, you're going, wow, why don't you use it 100% of the time? Well, think about it. Part of your time you have to be pumping to move the water back uphill. And so you can't always be generating. In typical numbers, you see about 20 to 25%, though those vary greatly from one location to another. This looks at storage in terms of, earlier we were looking at it, how it impacted curtailment. This is showing how it impacts it in dollars and cents. And so you can see, there's complementary areas there. As you add transmission up to a point, it increases the value of the storage. And so you see that there. But the interesting thing, and it's very nonlinear, so it depends on the system. We looked at the Western Interconnect, which is essentially Colorado West. But if you go to Copper Sheet, where you have all the transmission you could ever want, it actually kind of diminishes the value of the storage, because one of the things storage is really good at is buffering those transmission lines. This particular plot, we explored, does it matter where you site pump storage hydro? And the two scenarios we were looking at is, do you put it at the generating end or where the demand is? And on the left side, that's if you site it where the wind farms are. And you can see the value is quite a bit higher than if you were to put that same facility down where the load is located. And it makes sense when you think about it, just for the very reasons that I was talking about, the ability to make the best use of that transmission line to get it into Southern California, because that's where most of the load is in this particular case. And, it's quite a difference in terms of the value from just based on where you site it. And so it's really important to keep that in mind. And then the last result kind of for this first study was looking at, okay, how much revenue can you make from a facility? And, pump storage hydro has capital costs are actually similar to what batteries are. It depends on the duration. Longer duration, it's actually cheaper. Shorter duration, it's more expensive. But typical for an investor might be they'd want to pay back in 10 years. And so you take that number and you look at it, it's like $20 to $30 per kilowatt year, and compare that to what you can get in energy value alone. And what I mean by energy value is arbitrage. So, and what's driving this, why the energy value is low, is think about natural gas prices. They've pretty much, between the addition of a whole bunch of wind and solar, which are zero marginal cost things, so you really, when they're the last item on the stack, nobody's making money on the grid. And then when it's other things, such as most of the rest of generation at this point now is very, very natural gas heavy, and it's cheap. And so the takeaway from this particular work is you can't really justify storage on energy value alone, but there are a number of other services that the grid needs. Tom, mentioned ancillary services in particular, and then another real emerging area for, especially for something like pumped storage hydro that can have really high capacity, is just the capacity, the fact that it's there in case other resources don't show up. And just, this is kind of a summary through all of those, talking about how both pumped storage hydro and transmission can help reduce curtailment. And the really cool thing is if you use them together strategically, the sum of the parts is actually more, or the whole is more than the sum of the parts. So it's a very synergistic pairing of the two. But you got to be smart about it. As I mentioned before, there's some value of balancing. When do you use that storage to buffer transmission lines? Because if there's in areas where there are no transmission congestion issues, the value of storage is diminished. Okay, this is the second study, and I just wanted to bring it to your guys' attention because it's kind of fun from the standpoint of it looks at things, before we were looking at, moving wind to a load center. This one looks at kind of storage duration and what's the value of storage over time. And we upped the percentage here as far as the amount of variable generation, which is the same thing as renewable energy, and it's 55%. And for this system, it was roughly the size of ERCOT was the model used for this, and ERCOT is Texas. And we looked at 3 different scenarios. Chose the wind vision, so that would be familiar to people that work in the wind field. The other was kind of a trial and error where we would run to look at how do you minimize curtailment. And then the third is looking at an equal mix of wind and solar. And what this plot shows is the value, or kind of how curtailment is impacted by the duration of storage. And so you can see the 3 different scenarios that I talked about. And you can see right away, man, equal mix, high curtailment compared to some of the other 2. And this is a pretty common finding. If I just had to take a rough estimate in the West, it tends to be about 3 to 1 wind to PV, tends to be about optimal. But you can see, look at the slopes of the lines, and so they all have pretty strong slopes up to 4 hours and even out to 8 hours. But things start to flatten out as you start looking longer term. One thing I want to bring to your attention here, this is for a 55% renewable study, and as the amount of renewables on the system gets much, much higher, you see actually longer duration storage having higher values. Unfortunately, the research isn't quite to the point where I can release that yet to show you guys this, but this should kind of whet your appetite, showing me if there's some real potential here. But you do get to a point where the curve starts to flatten out. One of the nice things about this is hydro, or pumped storage hydro, when you want to increase the duration, it really means just making the reservoirs bigger. You don't have to buy all the additional equipment, like new different generators, things like that, which this differs greatly from a technology like batteries, where if you want to double the duration and have the same capacity, that means you have to buy twice as many batteries. And that's why I mentioned earlier, for longer duration stuff, pumped storage hydro tends to be quite a bit less expensive than batteries. Although, in fairness to batteries, their prices are dropping. So it'll be interesting to see how it plays out long term. Just so that you don't have to go to those plots and pick out numbers yourself, look at how the storage impacts curtailment. In the equal mix, that's something I wouldn't recommend anybody building out, but it's happened. You actually see it in California. You hear about the duck curve. They're probably a little overbuilt in solar. And so, look at 4 hours. You can reduce curtailment by 70% just having 4 hours of pumped storage hydro available. And then you get out to 8 hours, you're almost reducing curtailment by 90%. And then the last point is kind of, as I mentioned before, there is a balancing act. How long, really long duration storage can be helpful, but is it economic? Okay, and then the last study is one that, I wanted to mention, because this is an area, where we need future researchers. It's something that's happening really, really quickly. Think about, throughout the country, all the places with 100% renewable RPS standards, or places that are going to zero carbon. And to get there, it makes for a very different way. Right now, NREL is working with Los Angeles, and it's the Los Angeles Department of Water and Power. They have hired us to help them get to 100% renewables, and these are kind of the four main points that they think about. When these are the things they're asking about. Kind of the pathways and costs. How do you get there in a way that has minimal impact on the environment? So, because there's some technologies out there that you might be able to use, but what's their environmental impact? Is there something else that might be better? Like right now, it's kind of up in the air on pumped storage hydro and batteries in terms of if you look at overall footprint, but that's an area we're going to be doing research. And then there'll be economic impacts of this. And then the other one, the last one that was really important to them is kind of, they wanted everybody in the community to be able to participate. And what we're finding internally, and as I say, I wish the research were far enough along that I could have shared some of the results, but since it is for an outside client, they've asked us to hold back until it's released publicly. But we're seeing, as you get to 90%, I won't say that it's easy, but you can get there with kind of thinking similar to what we use today when we want to integrate large amounts of renewable energy. And so pumped storage hydro or batteries can really meet most of that demand. With batteries getting you past, like in the summer in Los Angeles, actually your peak load is right after the sun sets, but it can get you past those first 4 hours, and then you have enough pumped hydro to get you through the whole night. And as I mentioned, the real challenge for us now is getting that last 10%, because there's times, especially in summer, when loads in Southern California can be very, very high, but almost no wind. And so how do you get it from, through those wind lulls? Or, if you watch the news at all, it's hard not to miss all the fires in California. And when those happen, that takes out transmission. And you've seen the impact with kind of the, people as far as power going out. But this is a really cool area as far as for future research, because you can approach it from the perspective of engineering, or also a mix, because as you go to 100% renewable energy, think about it, what it does to the market. Everything then is zero marginal cost, and so the traditional least cost no longer works, and so we need some really cool research in that area as well. And so with that, I will just kind of open it up for questions, and so I'll hand it back over to Rob.
And that's a great presentation. Thank you, Tom and Greg, and absolutely much learning for us. And we saw that how wind and hydro work together to enhance value for each other. And it's also a good question for economics and the engineering perspective. And Greg showed us that high contribution of the renewable energy is possible. That's very exciting. And with that, and we are opening this floor for the question and answer. Please type your question or even speak out your question to our presenters.
Hello, this is Rob Larson from Montana.
Yes.
Just to check, can you hear me?
Yes.
Yeah, great presentation. I guess I really don't have specific questions other than availability of the slides for future use. Will those be available? Can we use these in our coursework?
The video of this is available, but I'll talk to the presenter and get back to you, Rob. Thank you.
Okay, thank you, Rob.
And I can see the couple questions in the comment box, and I'm gonna, I think Tom already answered some of them, but I'm gonna ask this question from Joshua to Greg. This is the question. Can you repeat the question for the audience? Where is this one?
Okay. Sure. The question here is, when it comes to operation, optimization, and control, are there ramping constraints and costs associated with changing power outputs? And then the question goes on to ask roughly how large are the constraints and costs? And on the first part of the question, yes, most definitely there are ramping constraints. On the production cost modeling, they have ramping constraints built into them so that you can only move so much, and then it has kind of min-gen, rough running zones, all those types of things to try to capture in those. And as far as cost, this is actually one of the burgeoning areas for research.
Greg, we lost your audio right when you started to answer the question about costs.
Okay, can you hear me now?
Yes.
One of the challenging areas of research right now is there's not a lot of information available on cost. Tom had mentioned the Columbia River Basin, and I know that's one area struggling where they're starting to use hydro differently, where you're seeing large swings, and they know that it's causing a tremendous amount of wear on the machine, but have a real handle on that. And so one of the industry utility groups is actually addressing that. Ciotti is putting together work to just those issues.
Yeah, we'll have probably time for a few more questions.
This is Tom. I'd like to answer a question for Greg. So the pump storage hydro looks like it could be a good option for some of the results that you were showing. How difficult is it to permit and build a pump storage hydro, or just to expand the reservoir? Do you have any idea?
That's actually what we're finding out now is kind of there's a resurgence because I'm guessing you're aware, but like PGE, Portland General Electric last year put pump storage on their IRP plan. But as far as how difficult, it's getting easier. They've done a fast track for closed loop pump storage for regulatory stuff. And then also now with kind of the restructuring as far as approvals, and I'm to remember the time frame, but now it used to be that any organization, they look at their assessment and then the next group starts with them, and now the government actually requires those to be done at the same time. So it shortens the timeline as far as getting regulatory approval as well.
That's great, Greg. And I see a lot of questions. I'm going to read the next question from Sarah. The question is, how much pump storage potential capacity are for future development?
I'm trying to think of, if I remember right, we're about 22 gigawatts. I don't know, Tom, get offhand.
I don't. But what I would do is go check that Oak Ridge National Lab Hydro Source website, because I think they've got an estimate there.
Yeah, they've done an assessment, and I just was looking at it. I wrote it up last week. I'm just trying to remember the number. I know it's at least an additional 50%, which would be another 11 gigawatts, kind of nationwide. But it may actually be higher than that. But what Tom referenced is actually a great site to look at.
I think we are right on the time, and I'll let you guys still ask the question in our comment box or chat room, and we'll forward those questions to the presenters and come back to you. And with that, we're gonna stop this presentation today, and I'll let Tom and Greg speak final words if they have any.
Tom, do you want to go ahead?
If I heard Rob correctly, I just get to say so long, and thanks everybody for your time today.
That works. And yeah, hi, this is Greg. I would just really encourage you to check out Pump Storage Hydro, because there's some really cool opportunities that are coming up as we get higher and higher penetrations of renewable energy on the grid. But thank you for your time.
Thank you very much, everybody. With that, we are going to stop this webinar today. Thank you very much. And we'll come back with recording of this video in about 2 weeks. Stay tuned. Thank you very much.